The next paper is Protection System Planning for Distribution Networks, a Probabilistic Approach, and it will be presented by Wandry Rodrigues. He received his Bachelor Engineering degree in 2018 and currently is a master's student at São Carlos School of Engineering of the University of São Paulo, Brazil. His research interests include planning and control of distribution power systems. Again, this presentation will go with the video presentation.
Hello everyone, my name is Wandry. I'm a master's student at São Carlos School of Engineering, and I'll be presenting the paper entitled Protection System Planning for Distribution Networks, a Probabilistic Approach. The protection system has the main function of maintaining or guaranteeing the security of the power system. But in distribution networks, we also have a secondary function. The reliability indexes are related to the operation of protective devices. So when planning a distribution system, we must consider where to allocate the protective devices, or the protective and the controlling devices, as a mean to increase the reliability indexes. We can't calculate or we can estimate the reliability indexes during the planning phase. However, we can do so only if we know or if we can guarantee that the protective devices would operate in a coordinated way. To verify coordination, we can rely on indications of coordination, or we can actually verify it using mathematical models. Both methods work when we consider a distribution network without generators. However, when we insert DGs, we can have mainly two problems for the protection system. First one, the loss of coordination. The allocation of a DG can increase the short circuit currents in the entire system. So a fault at branch 10 could cause the melting of this fuse and this fuse. And we would have two devices operating for a single fault, which decrease the reliability indexes. Additionally, we can have bidirectional current flow in some branches. So, for example, at branch 14, if we didn't have the DG, we could have a fuse. However, when we insert the DG, there is short circuit currents flowing through branch 14 for every fault in the system. So this fuse would melt for any fault at any point of the system. And again, we would be decreasing the reliability indexes. So even though this solution is valid if we don't consider DG, it is not valid when we consider the DG. And the indications of coordination are not enough, as we can observe here. So we need to verify the coordination. And we can do so after the allocation is complete or during the allocation. The first one is used by most of the methods found in the literature, but a second group of authors are investigating the coordination as a constraint for the allocation of protection devices. So in this method, we use a probabilistic routine or a probabilistic short circuit routine to possibly disregard some of the most rare short circuit scenarios. We propose the expansion of the protection zone of the reclosers as a means to represent better the real operation of a distribution power system. We consider the allocation and the coordination as a single optimization problem, and we consider the operation of islands and the load transfer between neighboring feeders as mean to increase the reliability indexes. About the probabilistic routine, we have 5 stochastic variables: the system loading, the power injection for renewable DGs, the fault location, the fault type, and the contact resistance of a fault. And every one of those variables is handled by a Monte Carlo simulation. And once we have all those variables, we can calculate the magnitude of the short circuit currents. We use a modified version of the hybrid compensation method first proposed by Zhang. However, in the first proposal, every DG is considered to be a synchronous machine. So it is a voltage source limited only by the path impedance. However, when we have inverter based DGs, they have controllers that limit their current injection, and therefore the Zhang method cannot be employed. So what we propose is the verification of a violation to the DG current injection, and if so, we set the DG current as its limit and remove it from the matrix Z and V, then calculate again matrix I until there is no violation, as proposed in Zhang. Once we have the short circuit currents, we can verify the coordination, the selectivity. So in our proposal, the dynamic of operation between two reclosers or two fuses is the same. The primary device must always operate first, and the rear guard only operates if the primary does not. The dynamic of operation between a recloser and a fuse is a little different. The recloser must operate in instantaneous operation faster than the fuse, but in the delayed operation, the recloser must be slower than the fuse. When involving a switch, we must consider that the switch is not a protective device. So the closest upstream protective device must operate. In this sense, in this example, we have here a maneuvering switch. And the first upstream device is the substation relay. So any fault occurring inside the protection zone of this switch would cause the protection relay here to operate. The dynamic involving an IID is simpler. There is no need for coordination nor selectivity. The IID must operate as fast as it can, and the other protective device as well. The expansion of the protection zone of a recloser can be explained in this figure. Considering the general rule, we verify the coordination between those two fuses and between this fuse and this relay, but not this relay and this fuse. So for a fault at branch 10, the substation relay would not operate, but this fuse would. So for a temporary fault, we would experience permanent interruption in those nodes. What we are proposing is this relay must sensitize for a fault in this region so that the temporary fault would not affect those nodes. Our proposition of optimization is the reduction of NSAC, SAIDI, equipment costs, considering the following constraints: allocation, coordination, voltage limits, current limits, and generation limits. And we use an SGA tool to solve the optimization problem. We have variable mutation and crossover taxes. We are implementing the integer codification. So 0 means there is no protective device. 1 means the allocation of a fuse. 2 means the allocation of a recloser or a relay. 3, the allocation of a switch. And 4, the allocation of an IID. In this approach, or in this paper, we are using this test system. It is a 135 real feeder, and we divided it in some regions. Those regions have different load density and different consumers density per node. Additionally, we have three types of consumers, and each consumer has a different cost associated with the energy interruption. So, considering this test system and 50,000 Monte Carlo iterations, we have this distribution for the short circuit currents at the substation branch. We can observe here that the most critical ones surpasses 2,500 amperes. But when we consider only 95% of those scenarios, the maximum short circuit current is lower than 2,000 amperes. And that makes it easier for coordinating fuses with reclosers, as we can observe here. Especially in this figure, we can observe that the red frontier dominates most of the blue frontier. That is, considering less short circuit scenarios allows us to find better solutions, at least considering those two objectives. It is important to analyze solution B and solution A. They both have virtually the same insects. However, solution B is far less expensive than solution A. The fundamental reason for that is the allocation of fuses in solution B, which cannot be verified in solution A, since solution A has very high short circuit currents in the lateral feeders, and solution B does not. So it is easier to allocate fuses in solution B. Since solution B can be more attractive to a distribution company, we provide details on solution B here. These regions are the load transferring rate regions, and the hatched areas are the islanding regions. We can observe here fault at branch 52, and we have multiple sources. What we are expecting is that fuse 50, or fuse at branch 50, would operate slower than every other device represented here in their instantaneous operation, and faster than those devices in their delayed operation. And we can observe that in this figure. Here we have the minimal melting time for the fuse, that is, the minimum time considering the maximum short circuit current flowing through the fuse. And we have here the substation relay instantaneous action, which is faster than the fuse. And we can observe the same for the three IIDs. So the fuse acts slower than the instantaneous actions of relays and IIDs. When we consider the maximum melting time, that is, the maximum time for the minimum short circuit current in the fuse, we have the IID's timed action slower than the fuse, and we can observe the same for the substation relay. And we can extend that for both phase and neutral units, which guarantees the coordination as proposed. Finally, we can observe here that this maximum short circuit current at branch 107 is not twice the short circuit current in branch 121, even though the power injection in this branch is more than the double of the power injection in this branch, which means we are limiting the current injection of the solar farm and the wind farm, which has impacts on the pickup currents of the IIDs. If we didn't do so, we could set those pickup currents too high and experience some loss of coordination depending on the fault scenario. In conclusion, our proposal provides solutions feasible considering technical and economic aspects. Our method to limit the short circuit currents in the inverter connected DGs has impacts on the pickup currents for the IIDs, which mitigates the probability or the chance of misoperation. And by disregarding some of the rare short circuit cases, we can have most cost-effective solution than we could when we considered every case scenario. Thank you very much. I'm open to questions. Thank you.
Thank you. And it seems that we have one question. It's from Felipe Lopes. What kind of DG have you considered in your study?
Okay. We considered three types of DGs. The first one, named DG in the figure, is a synchronous machine. And the other two, we consider inverter-based DGs, solar farm and a wind farm.
Thank you. And just another question. When you compare the costs, could you just give us a ballpark of how cheaper your solution is?
Could you repeat the question, please?
You said that your proposal, it's not only technically feasible, but more economically feasible. I was wondering if you had a number of this, how much or how less money would expand? Would be like 1/3 of the other solution, 1/5?
I see. The thing is, we are using an NSGA, right? So we have at the end a tier of solutions. We have solutions, all of them feasible. So the user can select which one they want to employ. For solutions A and B, which we presented on this paper, we have a difference of $50,000 between those solutions. So I hope that answers your question.
Okay, thank you. Thank you.